Let's do some calculations regarding weak acids and bases. First, let's understand that in first-year chemistry they keep things strong since things are a little bit easier. For example, if we have a strong acid such as HCl being 0.001 molar, we can say immediately, you should notice that the pH is going to be 3, since that is the negative log of 10 to the minus 3 is 3. You should also notice that since it's hydrochloric acid, that means that concentration is the same as the H plus concentration. Remember, it's not an acid till it forms H plus. Strong acid, so the total dissociation, and that is your H plus concentration, 10 to the minus 3 molar. Take the negative log, and you get a pH of 3, and it seems reasonable since that's an acid. A 0.02 molar barium hydroxide solution, we can do a similar analysis. So what can we say about that? Strong base, so it's totally dissociated. Is the concentration of hydroxide 0.02 molar? No, it's going to be twice that. It's two ions of OH minus form for each molecule. So there they are. There's two of them. So we have a 0.04 molar hydroxide. Let's take the negative log, but remember when we do that, we don't get the pH, we get the pOH, which is 1.4. And 14 minus that gives us the pH, which is 12.6, and that's reasonable for that base. However, when you got weak acids and weak bases, they're not totally dissociating. Some dissociate a lot, some dissociate a little bit. The value used is the ionization constant K. Less than 1 is weak, greater than 1 is strong. But if you take a look at some typical values, you'll see that the highest one in this list is a 1/10,000. So we have nice low numbers showing these things having a very low Ka. They went ahead and calculated the conjugate base, Kb, as well. Let's focus on just this Ka for now. These are relative from -4 to 10 to the minus 10th. So they're just dissociating a little bit. We can calculate the equilibrium concentration by multiplying the products over the reactants, and that'll give us the Ka value. Let's go ahead and solve the problem. You have a 0.36 molar nitrous acid solution, and the Ka is 4.5 times 10 to the minus 4. Let's try to do this a quick way without an acid table. First, let's write what's happening. Nitrous acid gets thrown in water. What's in the flask? Mostly just nitrous acid because it's got a very low dissociation constant. But a little bit of H plus, a little bit of NO2 minus. If we can find out H plus, we can get the pH. The negative log of that concentration will be equal to it. We can set up the equilibrium constant expression as products over reactants. And what do we know? Well, initially this was nothing, but at equilibrium each one will go up by a value of x, so we can write x squared on the top. Initially this was a value of 0.36 molar, so we can do 0.36 minus x. Since the concentration at K is very low, we can approximate that as 0.36, giving us 4.5 times 10 to the minus 4 equals x squared over 0.36. We should be able to solve for x. We get that it is 0.000763. Taking the negative log gives us the pH, and we're done. No ice table. Here it is with the ice table. Very similar. Write the chemical reaction that's occurring when this thing dissolves. Write down what you know about the initial concentrations. Notice we have nothing initially. Think about the change in terms of ratios. This will go down by a certain number of molecules. These will go up by the same number of molecules because it's a 1 to 1 to 1 ratio. We make the approximation that we can make right here, call that 0.36, and we get the same answer. You can check the approximation if you want to. I simply am going to say that the Ka is very small, so we can make that approximation, and the pH is 2.11. Let's do another problem that's just a little bit harder. They tell you the pH of a 0.1 molar solution of formic acid, and it's 2.39. That means we do know the hydrogen ion concentration. 10 to the negative pH will be that number. From that, can we get the Ka? Well, let's set things up. We're talking about dissociation of formic acid. You're throwing it in water. So that means that it's forming the anion and H plus to a small extent. And we can write down the equilibrium constant expression like we always do, and then we can think about what we know. 10 to the negative pH is this concentration right there. And for every one of these that forms, one of those forms as well, see? So it'll be the same for that. So we'll take whatever number this is and we'll square it. And do we know what this concentration is? It's 0.1 molar solution, 0.1 molar originally. It'll go down by a value of x, but we'll ignore that because of our approximation that we always make. And we simply get that once we get the H plus concentration, we find out that we square it, and there it is. Ah, look, we don't have to make the approximation. We know exactly how much it went down from, right? It went down from by 0.0407 molar, so we might as well subtract that from the original H plus concentration. That's right. So we get a nice precise answer here. And we haven't come up with a final number, but let's do it when we show the slower ice table method, right? Let's see. Initially it was 0.1. It goes down by 0.00407 since we know the pH. That must be H plus concentration. And we subtract that from 0.1 molar to get this concentration. Plug them all in, get a final number. 1.73 times 10 to the minus 4th. That sounds like a nice typical Ka value for a weak acid. Okay, that's a little bit about weak acids and some calculations for them, including 2 sample calculations.